All right, so today we're going to work some of these AP problems that we're not going to have time to get to in class, so I expect you guys to watch this and know you're responsible for this information as well. This is just applying what we've learned. So this first problem, these are straight from old AP exams. You can tell by the font they're really old AP exams. So part A, from the systems above, identify the conjugate pair that is best for preparing a buffer with a pH of 7.2. Explain your choice. So what we're going to focus on in Part A is assuming we're making an effective buffer. And if you remember from class, an effective buffer is a buffer where the pH is equal to the pKa because, remember, this ratio of ion to acid ends up being 1, so the log of 1 is 0. So we get something where the pH is equal to the pKa. So we have the Ka for 3 different systems. And if I were to take the p, or the negative log of all of these, I end up with a 6.38 here, a 7.21 here, and a 1.89 here. And therefore, the best system for this would be choice 2. All right? So, Part B. Explain briefly how you would prepare the buffer in solution A with the conjugate pairs you have chosen. So, how I would make the buffer, I would take a 1-liter flask and put equal moles of my H2PO4 minus, but I can't find H2PO4 minus on the shelf. I have to get it in salt version. NaH2PO4 minus, NaH2PO4, excuse me, and my other HPO4 minus 2, it would be Na2HPO4. So I take equal moles of both those salts and fill to the line. By putting equal moles in 1 liter, I'm basically making equal concentrations. So again, my pH would be equal to my pKa, and that would be the correct pH. Part C. If the concentrations of both the acid and the conjugate base you have chosen were doubled, how would it be affected? Well, think about that ratio. Remember, I'm just doing the ratio portion of it. The log of HPO4 minus 2 concentration over H2PO4 minus is the ratio we're looking at in that second system. If I were to just double both of these, and since they're the same, well, it doesn't matter, the same or not, if we double both, we get a proportional change where the ratio doesn't change. The ratio doesn't change. pH doesn't change. Correct? All right. And Part D, explain briefly how you would prepare the buffer of a solution in A if you had available the solid salt of only one member of the conjugate pair and solution of a strong acid and a strong base. So basically, we're forcing an invasion here in order to make the conjugate. So let's think about it. I'm just going to say, let's pretend we have a strong acid. If I have HCl, I need to pick which salt of those two am I going to use to make the buffer system. So if I add H plus to HPO4 minus 2, do you see how that makes H2PO4 minus? Correct? It just jumps on there. That then is our buffer system. So how much am I going to invade by? I'm just arbitrarily choosing. Let's say I have 4 moles of this. I'm going to add it to 8 moles of this. And again, this is kind of like a stoic table. Think about it as a stoic table. And you'll see why I'm choosing that in a second. If this is going to run out first, we're going to create 4 here. And so I end up with 4 moles of each of these in the same volume container. Same moles gives me where the pH is equal to the pKa, right? And that's what we're looking for. So the trick to these problems when you want to create a buffer from something strong, you want to add enough strong to neutralize half of your acid or base. So let's just do the reverse version really quick of the other one. If we were to add the OH minus, say we had a strong base at our disposal, we'd add it instead to the other salt, and we'd get HPO4 minus 2 plus H2O. And again, if we have 10 moles of this, I'm going to add 5 moles of that to neutralize half of it. Lose 5, lose 5. Again, this is just another stoic table. So I would have 5 moles and 5 moles of my acid and my conjugate base in the same container. All right? And that would give me, again, pH is equal to the pKa. So that's how I would handle part D. And if you have questions about that, you can come ask me. Let's move on to the next problem. In water, hydrozoic acid, HN3, be careful, that is not ammonia, is a weak acid that has a Ka equal to 2.8 times 10 to the negative fifth. A 0.3 liter sample of 0.05 molar solution of the acid is prepared. Write the expression. So before I can write an expression, I'm going to go ahead and write, because I know I need it for part B, I'm going to go ahead and write my reaction. I'm going to take my acid. Since it's a weak acid, to find the pH, I always add it to water, and I get N3 minus plus H3O plus. That's where I'm going to get my expression from. So my Ka then is equal to N3 minus times H3O plus divided by HN3. And there's my Ka expression. Part B says to calculate the pH. Again, classify what you have. Weak acid. So I put it in a rice table, and I know that I have, it says I have 0.3 liters. I don't care how much I have. What's important is that it's 0.05 molar, 0, 0, minus X plus X plus X. 0.05 minus X, it's going to be negligible, X and X. I'm going to plug it into my expression with the Ka that they give me of 2.8 times 10 to the negative fifth and equals X squared over 0.05. I know I'm moving fast, but you have a video, so you stop it after every step and make sure you get stuff copied down and understand what's going on. All right, I'm going to solve for my X. I get an X equal to 0.001183, which is equal to the H3O plus concentration. If I take the negative log of that, I end up getting a pH of 2.93, which is what part B is asking us for. All right, now part C and D, I don't want you to freak out. I just want you to realize they're taking the 0.3 liter and they're doing two different things to it. They're doing part C to it, and then they're doing part D to it. So they're taking half of it, messing with it in part C, and then taking the other unused half and messing with it in part D. So these two, part C and D, are unrelated, and they relate back to the original weak acid. So taking a look at part C, the question says 2.15 liter of the solution, 0.80 grams of sodium azide, NaN3 is added. So I've got my weak acid, which is HN3, hanging out. And remember, what is that molarity? 0.05. And this is actually 0.15 liters of it. To it, I'm going to add 0.8 grams of NaN3 minus. Well, what's important about that is the fact that we're adding the conjugate base to that acid. Remember, Na is a spectator. So if you notice, by adding this conjugate to the original, aren't I making a buffer because I have a weak acid and its conjugate base? Yes, I'm making a buffer. So if I'm going to figure out the pH of a buffer, I need Henderson-Hasselbalch, right? Plus the log of the concentration of the ion over the concentration of the acid, HN3. Correct? Correct. All right. So now I know the concentration of the acid because it's my original concentration of 0.05. But what I need to find is the concentration of that N3 minus. Well, remembering this N3 minus was actually Na3N. I've looked up the molar mass to that, and that's 65.02. NaN3, sorry, my bad. NaN3, that's not right. Yeah, NaN3, that is right. This comes out to be 65.02 grams per mole. Even if it's wrong, we're going to use it. All right, so I know grams, I know moles, and now I'm going to figure out the molarity by doing, I'm just going to come over here, moles per liter, right? Well, my moles, 0.8 divided by 65.02 gives me moles, divided by the full liter. Oh, how many liters did I have? 0.150 liters. So I'm going to get my calculator here because I didn't do this step before. And I get 0.8 divided by 65.02, divide that by 0.150, and I get a concentration of 0.082. So 0.082. So now all I have to do is plug in chug. pH is equal to the negative log of the Ka of 2.8 times 10 to the negative fifth plus the log of 0.082 divided by 0.05. So when I do this, and I hope I get it right so I don't lead you all astray, negative log of 2.8 times 10 to the negative fifth plus the log of 0.082 divided by 0.05. I end up getting a pH 4.77. Yay! So that is part C. And the last part, we're going to go back to our original acid and take that other remaining 0.15 liter, and this time we're going to add, we're adding 0.075 liters of something strong. So we're adding something strong to a weak acid. And what is adding something strong to a weak acid? It's an invader problem. So how do we start invader problems? With a Stoich table. We're adding sodium hydroxide to that original acid, correct? And that makes H2O plus N3 minus. So right now I am just doing a Stoich table. So in the Stoich table, I'm looking at moles of everything. My moles of NH3 I find by taking the original 0.05 molar and multiplying it by the 0.15 liters, because that's how much we use, so we get a 0.0075 moles of this. And then to find moles of base, I take my 0.075 liters of 0.1 molar, multiply 0.1 times 0.075, to get 0.0075 moles of base. So I'm having equal moles. Now everyone's like, oh, it neutralizes. No, it doesn't, because we lose all that. But what do we gain? We gain a salt here. Bam, bam. So now I have 0.0075 moles. So after the war is done, they've battled out, our war is complete. What do we have left over? Left over, it's a hydrolysis problem, right? So before we can actually start the whole process of doing the hydrolysis, we need to get this to concentration to put it in a rice table. So my 2 liters, first from the original acid and then from the base I added to it, is that many liters. So when I solve for that, I get a 0.0333 molar solution. 0.0333 molar. Now I'm going to do my hydrolysis problem, which you already know how to do, and put it into a rice table. Rice. So I take my, what's left over after the war, that's all that's left. These guys are gone. Add it to water, and I get HN3 plus OH minus, and I have an original concentration of this of 0.0333 00 minus X plus X plus X. So I get 0.0333 minus X, X and X. Get rid of that guy. And so I have X squared over 0.0333 is equal to, this is a KB. So I got to take the KW divided by the KA they gave us and get 1e negative 14 divided by 2.8 times 10 to the negative fifth. I'm going to cross multiply and solve. And when I do, I get x is equal to 3.65 times 10 to the negative 6 moles per liter. Now that's equal to x, which is equal to the OH minus concentration. The problem says calculate the OH minus concentration. So that's all we had to find. We didn't have to take it to pH. Okay? I know that was fast, but again, I need you to, if you've got to go back and stop after every part, I need you to understand this, and then if you still don't get it, please come ask me questions. This is a level of problem that will happen on the AP exam, and I want you guys to be ready. So have a great evening.